Imagine a time long before satellites, before telescopes, before even the idea of modern science had taken root. Now, picture a group of sponge divers in the year 1900, battling the currents off the small Greek island of Antikythera. One diver surfaces, shaken, speaking of a horrifying sight below, a heap of rotting corpses and horses on the seabed. But what he had actually seen was not a graveyard, but something far more extraordinary. It was the ghostly remains of a massive Roman-era cargo ship, a time capsule from the 1st century BCE that had rested undisturbed for 2,000 years. Its precious cargo of marble statues, glassware and jewelry scattered across the ocean floor like fallen stars. This was the Antikythera Shipwreck, a discovery that would rewrite our understanding of the ancient world. The importance of this wreck cannot be overstated. It wasn't just another sunken vessel. It was a snapshot of a vibrant, interconnected Mediterranean world. Lying at a depth of 150 to 230 feet, the cold, dark waters had acted as a remarkable preservative, protecting materials that would have long since vanished on land. This underwater archaeological site became a portal, allowing us to step directly into the past. For over a century, explorers and scientists have returned to this hallowed ground, slowly and carefully piecing together the story of its final fateful voyage. Each artifact brought to the surface is a word in a long-lost language, speaking of art, commerce, and a level of technological sophistication we once thought impossible for the era. The initial discovery was just the beginning of a long and challenging journey of exploration. Early efforts were more akin to treasure hunting, focused on retrieving the most spectacular items, like the beautiful bronze and marble statues that now grace the National Archaeological Museum in Athens. However, as archaeological methods evolved, so did the approach to the wreck. Modern expeditions, like the one that returned to the site in 2025, are no longer just looking for treasure. They are forensic investigators of the deep, using advanced robotics and meticulous documentation techniques to study the ship itself, its cargo, and the very context in which it sank, revealing the intricate web of ancient life. This shift in focus from mere objects to the story they tell is crucial. The recent confirmation of a second vessel from the same period, located just 650 feet away from the main site, opens up even more tantalizing questions. Was this part of a convoy? Did one ship try to rescue the other in a storm? The Antikythera Shipwreck is not a static monument. It is an active crime scene, and the detectives are the archaeologists, patiently sifting through the evidence. They are not just recovering artifacts, they are recovering history. A history far more complex and brilliant than we ever dared to imagine, hidden beneath the waves for 2 millennia. The cargo of the Antikythera ship tells a story of immense wealth and cultural exchange, a floating marketplace of luxury goods traversing the busy highways of the ancient sea. Imagine the ship's hold, packed to the brim with marvels from across the Greek and Roman worlds. Archaeologists have documented an incredible array of items that paint a vivid picture of its journey. Recent excavations alone catalogued around 300 new finds, including dozens of delicate ceramic shards and the heavy, elegant forms of amphorae, the clay shipping containers of antiquity. These weren't just simple pots, they were branded, telling us they came from distant ports like Chios and Rhodes, carrying wine, oil, or other valuable commodities across the vast Mediterranean expanse. Among these finds, the discovery of mastic resin used as a sealant inside some of the amphorae offers a fascinating glimpse into the practical details of ancient commerce. This sticky, aromatic substance, harvested from trees on the island of Chios, was prized for its preservative qualities. It ensured that the contents of the jars would arrive at their destination fresh and unspoiled after a long and perilous journey. It's a small detail, but it speaks volumes about the care and expertise that went into long-distance trade. These merchants weren't just throwing things on a boat, they were masters of logistics, using the best available technology to protect their valuable investments and satisfy the demands of a discerning market. But the cargo was not limited to everyday goods. The ship was also carrying a spectacular collection of art destined for a wealthy Roman patron. Divers have recovered magnificent bronze statues, including the famed Antikythera philosopher, and numerous fragments of marble sculptures. The 2025 expedition added another 21 marble pieces to this puzzle, each one a clue to the masterpieces that were lost. This was not just trade, this was the movement of culture itself. Greek art and philosophy were in high demand in the burgeoning Roman Republic. And this ship was a vessel of that intellectual and artistic transfer, carrying the very soul of Greek civilization to its new center of power. The sheer diversity of the cargo, from fine glassware and jewelry to massive works of art and humble storage jars, reveals the complexity of the ancient economy. It shows us a world that was deeply interconnected, where a ship could be loaded with goods from multiple ports across the eastern Mediterranean and be bound for a new life in Italy. The Antikythera ship was a microcosm of this globalized ancient world, a world driven by commerce, a thirst for luxury, and the relentless human desire to connect, to share, and to possess the beautiful and the exotic. Its sunken remains are a testament to the ambition and the reach of these ancient mariners. Beyond the dazzling cargo, the ship itself is a masterpiece of ancient engineering, and its preserved fragments are a textbook on shipbuilding. The recent discovery of a section of the hull, complete with its original fasteners and a protective lead sheathing, has given scientists an unprecedented look at how these massive vessels were constructed. The builders used a technique known as shell-first build, a method that dominated Mediterranean shipbuilding for centuries. This means they meticulously assembled the outer planks of the hull first, creating a smooth, strong shell, and only then did they fit the internal frames and ribs to provide structural support. It's a bit counterintuitive to our modern way of thinking, but it was incredibly effective. The true genius of this construction method lies in the joinery. The planks were not simply nailed together, they were interlocked using a system of mortise and tenon joints. Imagine thousands of precisely carved rectangular holes, or mortises, cut into the edge of one plank, and thousands of perfectly fitting wooden tongues, or tenons, carved into the edge of the next. These were fitted together and then locked in place with wooden pegs, creating an incredibly tight and rigid hull. This painstaking process required immense skill and precision from the shipwrights, who were more like cabinet makers than simple carpenters. The result was a vessel that was both flexible enough to withstand the stresses of the sea and strong enough to carry hundreds of tons of cargo. To make the hull watertight, the builders sealed the seams with pitch, a black tar-like substance. Furthermore, the entire outer hull was covered with a thin layer of lead sheeting, fastened with copper nails. This sheathing served a dual purpose. It provided an additional layer of waterproofing, and more importantly, it protected the wooden hull from shipworms, a marine boring creature that could riddle an unprotected ship with holes and destroy it in a matter of months. This combination of advanced woodworking, chemical sealants, and protective metal cladding demonstrates a profound understanding of material science and the harsh realities of the marine environment. These weren't just boats. They were sophisticated technological systems designed for durability and longevity. By studying these preserved sections, we can digitally reconstruct the entire vessel and understand the principles that guided its design. These weren't clumsy, primitive barges. They were the ocean liners of their day, the product of centuries of trial, error, and accumulated knowledge. The Antikythera ship represents the pinnacle of a shipbuilding tradition that made the epic voyages of the Greeks and Romans possible. It allowed them to build empires, to connect cultures, and to transport not just goods but ideas, art, and innovation across the known world. The ship was the engine of its era, and in its sunken timbers, we can still hear the echo of that powerful engine. Amidst the stunning statues and priceless artifacts pulled from the wreck, one object initially seemed unremarkable. In 1901, divers brought up a corroded, calcified lump of bronze, mistaken at first for a rock or a piece of a statue. It was set aside and largely ignored for months in the National Archaeological Museum in Athens. Then, something incredible happened. The lump split apart, revealing something that should not have been there. A complex assembly of interlocking bronze gears like the guts of a modern clock. This was the Antikythera Mechanism. No one knew what it was, but it was clear that it was something extraordinary, a piece of technology completely out of time. This single discovery shattered our preconceived notions of ancient capabilities. For decades, scholars believed that the ancient Greeks, while brilliant philosophers and mathematicians, lacked the engineering know-how to create such intricate mechanical devices. The prevailing view was that this kind of precision gearing didn't appear in history for another 1,000 years, in the astronomical clocks of medieval Europe. The Antikythera mechanism was an anomaly, an inconvenient truth that forced a complete re-evaluation of the history of science and technology. It was, as Professor Tony Freeth of UCL later described it, a creation of genius, the world's first known analog computer. The initial analysis of the device was incredibly difficult. It was broken into 82 fragments, many of them paper-thin and covered in inscriptions that were almost impossible to read. Early researchers could only guess at its function, proposing it might be a navigational tool or some kind of astronomical device. But without the ability to see inside the corroded layers, its true purpose remained a profound mystery. It was a puzzle box from the past, and for the better part of a century, its secrets remained locked away within its bronze shell, challenging generations of historians and scientists who dared to understand its meaning. The specialness of the Antikythera mechanism lies in this very challenge it presents to our historical timeline. It's not just a clever gadget, it's a testament to a lost lineage of scientific thought and mechanical engineering. Its existence implies that there was a whole tradition of creating such devices that has been almost entirely wiped from the historical record. The ship that carried it sank, but in doing so, it preserved this one miraculous survivor. Finding the mechanism was like finding a smartphone in an Egyptian tomb. It was a jolt that told us the story of human ingenuity was far richer and more complex than we ever knew. So, how did this ancient computer actually work? At its heart, the Antikythera mechanism was a mechanical model of the cosmos, a portable planetarium that used a brilliant system of hand-cranked gears to chart the movements of the heavens. When a user turned a knob on its side, dozens of gears, some with meticulously calculated numbers of teeth, would whir into motion. These gears were connected to a series of pointers on the front and back dials of the device, which was housed in a wooden case roughly the size of a shoebox. Each pointer tracked a different celestial body or cycle, all moving at their correct relative speeds, creating a dynamic map of the sky. The front dial was the main display, a stunning representation of the Greek cosmos. At the very center was the Earth, as the Greeks believed the universe was geocentric. Around it, pointers showed the position of the Sun, the Moon, and the 5 planets that are visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. These pointers moved along a ring marked with the 12 constellations of the zodiac, showing exactly where in the sky each body would appear on any given day. Another ring represented the 365 days of the Egyptian calendar, which was the standard scientific calendar of the time. By simply turning the crank, you could wind time forward or backward and watch the planets dance. The true genius of the design, revealed through modern imaging techniques, is its incredible complexity and efficiency. The engineers who built it faced a huge problem. The planets don't move in perfect circles. To model their irregular motions, the creators used a pin and slot mechanism, where one gear would turn another not from its center, but from an off-center pin moving within a slot. This clever trick varied the speed of the output gear, elegantly mimicking the apparent speeding up and slowing down of planets in their orbits. This is a level of mechanical sophistication that historians thought was invented during the Renaissance. Yet here it was, ticking away in the 2nd century BCE. Furthermore, the mechanism was designed to be incredibly compact. The engineers used shared gears and nested concentric tubes to display multiple outputs without them getting in the way of each other. Think of it like the hands of a clock, where the hour, minute, and second hands all rotate around the same central point without colliding. The Antikythera mechanism did this for the Sun, Moon, and planets. It was a masterpiece of mechanical information design, translating complex astronomical theories from Babylonian and Greek science into a tangible working model. It was, in every sense of the word, a computer forged in bronze. The Antikythera mechanism was more than just a model. It was a predictive engine. It was designed not just to show the state of the cosmos now, but to calculate its state in the past or future. A user could ask it questions like, when will the next full moon occur? Or, where will Mars be in the sky 3 months from now? By turning the crank until the date pointer reached the desired day, all the other pointers would automatically move to their correct positions, providing an instant answer. The device even had a small rotating sphere on the moon's pointer that was half black and half white, which turned to display the correct phase of the moon for any given date. The inscriptions found on the device's bronze plates acted as a user manual. They weren't just labels, they were detailed explanations of what the user was seeing. For example, next to the planetary dials, the inscriptions describe significant events in each planet's cycle, such as when it would appear to reverse its course in the sky, an event we call retrograde motion. The user could count the days between these index marks on the dials to know exactly when to look for these celestial phenomena. It transformed the sky from a confusing jumble of lights into an ordered, predictable system, a celestial clockwork that could be understood and anticipated. The choice of gear ratios reveals an astonishing level of astronomical knowledge. The Greeks had inherited centuries of observational data from the Babylonians and had developed their own sophisticated mathematical theories to describe planetary motion. To build the mechanism, the engineers had to translate these complex cycles into gear tooth counts. For example, they knew that Venus completes approximately 289 cycles of appearing and disappearing in the sky over 462 years. The engineers had to find a combination of gears with manageable tooth counts that would accurately replicate this ratio. The solutions they found are a testament to their mathematical brilliance and practical engineering skill. This device would have been incredibly powerful. For an astronomer, it was a research tool to check calculations. For a priest or civic leader, it was a way to align religious festivals with celestial events like the full moon. The back dials even included a calendar of major athletic events like the Olympic Games, linking human society to the grand cycles of the cosmos. The Antikythera mechanism wasn't for telling time in the way we do. It was for understanding our place within time, for seeing the intricate connections between our lives on Earth and the silent, majestic dance of the planets, sun and moon above. Perhaps the most spectacular function of the Antikythera mechanism was its ability to predict eclipses. On the back of the device were two large spiral dials. The upper dial was a 19-year calendar, known as the Metonic cycle. The ancient Greeks knew that every 19 years, the phases of the moon would fall on the same days of the solar year. This dial allowed a user to reconcile the lunar calendar, which most Greek city-states used, with the solar year. But its true magic lay in its connection to another deeper cosmic cycle, the Saros cycle, which was displayed on the lower spiral dial. The lower dial tracked the 223-month Saros cycle, a period after which the Sun, Moon and Earth returned to nearly the same relative geometry. This is the master cycle for predicting eclipses. An inscription on the dial indicated which months within this 18-year, 11-day and 8-hour period were likely to have a solar or lunar eclipse. Glyphs next to the month names specified the type of eclipse, S for solar, L for lunar, and even the time of day it was expected to occur. This was the ancient world's eclipse warning system, a way to know years in advance when the sun might vanish from the sky or the moon might turn blood red. To make these predictions accurate, the mechanism had to account for something subtle, the moon's wobbly orbit. The path of the moon is tilted slightly relative to the path of the sun. Eclipses can only happen when the moon crosses the sun's path, the ecliptic, during a new or full moon. These crossing points are called lunar nodes. The mechanism modeled this with a special pointer on the front dial known as the dragon hand. This pointer tracked the rotation of the lunar nodes, which complete a full cycle every 18.6 years. An eclipse was only possible when the dragon hand, the sun pointer, and the moon pointer all lined up. Imagine the power this knowledge would give you in the ancient world. Eclipses were often seen as terrifying omens, signs of divine anger or impending doom. A person with the Antikythera mechanism could stand before a crowd and not only predict the event, but explain it as a natural, repeatable cycle of the heavens. It was a tool that replaced fear with knowledge, superstition with science. It demystified the cosmos, showing that it operated on understandable principles, not the random whims of the gods. The eclipse predictor is perhaps the most profound statement the mechanism makes about the intellectual ambitions of its creators. The journey to understand the Antikythera mechanism has been a scientific epic in its own right, a story of technological detective work spanning more than a century. Because the original artifact is so fragile and fragmented, scientists could not simply take it apart. Instead, they had to find non-destructive ways to see inside. In recent decades, this has led to the use of incredibly advanced imaging technology. Researchers have used techniques like microfocus X-ray computed tomography, which is like a hospital CT scanner, but far more powerful, to create a complete three-dimensional model of every single gear and fragment, right down to the individual teeth. This high-tech imaging did more than just reveal the gearwork. It also allowed scientists to read the thousands of characters of text inscribed on the device's surfaces, text that was completely invisible to the naked eye. These inscriptions were the key that unlocked the final secrets of the mechanism. They were the instruction manual, explaining the cosmos it modeled. By combining the physical evidence of the gears with the astronomical information in the text, a team at University College London was able to create the most complete digital and physical reconstruction of the device to date, solving a puzzle that had perplexed science for over 120 years. Building these modern reconstructions is a process of reverse engineering. Scientists and engineers use the data from the scans to create computer models, testing how the gears fit together and what astronomical ratios they represent. They then use modern workshop techniques to machine new bronze gears, assembling them piece by piece to create a working replica. When the crank is turned and the pointers move, perfectly tracking the planets and predicting eclipses just as the original did, it is a moment of profound connection with the past. It is a way of shaking hands with the ancient Greek genius who first designed and built this extraordinary machine. From these reconstructions, we have learned just how sophisticated ancient Greek engineering was. We've seen how they used clever mechanical tricks to model complex astronomical phenomena, how they balanced mathematical accuracy with mechanical feasibility, and how they designed an elegant and surprisingly user-friendly interface. Each time we build a new replica, we learn more about the choices the ancient engineers made and the depth of their understanding. Rebuilding the Antikythera mechanism is not just an academic exercise, it is an act of resurrection, bringing a lost world of scientific innovation back to life. The Antikythera mechanism is more than just an ancient artifact. It is a manifesto. It declares that the universe is not a chaotic, unknowable mystery, but a system governed by rules, a grand and intricate clockwork that can be understood and modeled by the human mind. It represents a fundamental shift in thinking, a move away from mythology and toward a scientific worldview. The creators of this device were not just building a gadget, they were expressing a philosophy, a belief in the power of observation, mathematics, and logic to unravel the secrets of the cosmos. It is the spirit of science, cast in bronze. This discovery forces us to ask a tantalizing question. What else have we lost? The mechanism's sophistication suggests it was not a one-of-a-kind invention, but likely the culmination of a long tradition of mechanical engineering that has otherwise vanished from the historical record. Were there other similar devices? Perhaps even more complex ones? The sinking of the Antikythera ship was a tragedy, but the preservation of the mechanism was a miracle. It serves as a powerful reminder that history as we know it is an incomplete story, written from the fragments that happen to survive. There are missing chapters, and the mechanism is a glimpse into one of the most brilliant of them all. The Legacy of Antikythera is a lesson in human creativity. It shows us that there is no linear upward march of progress. Knowledge can be gained, and it can be lost. The technical skills required to build the mechanism were not surpassed for over a millennium. Its existence is a humbling reminder that brilliance is not the sole property of our modern age. It is a testament to the timeless, universal human drive to explore, to understand, and to create tools that extend the reach of our minds. The same curiosity that drove the ancient Greeks to build a mechanical cosmos is the same curiosity that drives us today to send rovers to Mars and build telescopes that peer back to the dawn of time. Ultimately, the Antikythera mechanism is a story of hope and inspiration. It shows us what humanity is capable of when we apply our intellect and ingenuity to the great questions. It is a small box that held the entire universe as they knew it, a universe you could hold in your hands and turn with a crank. It connects us directly to the mind of a long-lost genius, an anonymous Greek scientist who looked up at the stars and decided not just to wonder, but to build. And in the silent turning of those ancient gears, we can still feel the echo of that audacious, brilliant, and deeply human ambition.